we present our work AE2VID, Event-Based Video Reconstruction via Aperture Modulation. Our work proposes a method to reconstruct high-quality video from event camera data using dynamically modulated apertures. In existing methods, event cameras handle the reconstruction problem with motion-triggered events, which are usually sparsely distributed along the moving edges. By contrast, aperture modulation triggered events are dense and provide information across the entire scene. Combining these dense events with sparse motion events enables better reconstruction of static backgrounds. When the aperture opens, the event camera records these aperture modulation triggered events. Using our AENet network, intermediate dense intensity frames and hidden states are generated. This allows us to capture static background information in a very short period without losing motion details, thanks to the high temporal resolution of event cameras. Then our AE2VID framework uses AENet to fuse these dense intensity frames and hidden states with motion-triggered events to reconstruct final video frames. This approach improves background reconstruction compared to existing methods like AE2VID. And triggering can be modeled using a logarithmic intensity change model with stochastic dark current noise. Then we can integrate motion-triggered events to reconstruct video. However, using only motion-triggered events leads to an ear-post problem since the reference irradiance is unknown. So, we introduce aperture modulation triggered events. Aperture can change the global transmittance of the optical system, thus triggering dense, intensity-dependent events. T star be the time step of FPE, then we have this equation. So we can estimate the intensity I max using FPE. Here is a pipeline overview. Pipeline captures both aperture-modulated and motion-triggered events for each time interval. AENet processes aperture events to generate dense intensity frames and hidden states. AENet combines motion events with AENet outputs to produce a sequence of final video frames. This two-stage process ensures accurate reconstructions. Here is a detailed pipeline. It has two stages, AENet and MENet. Our AENet consists of three modules, FIR, IDN, and HSG. AENet first reconstructs an initial frame using FIR based on the first positive events. IDN denoises this initial frame from FIR. Finally, HSG generates hidden states and pseudo frames from a frame voxel, providing necessary inputs for MENet. We take the hidden state and motion-triggered events as the MENet input to reconstruct video. We first convert the event stream into multiple voxel grids. Then we process them using forward and backward processes to produce intensity predictions. Finally, we design a mixer module to combine the initial, terminal, forward, and backward frames, weighting them to produce the final video output. The framework is supervised with three losses: HSG loss to maintain hidden state quality, restriction loss to ensure accurate frame reconstruction, and time consistency loss to enforce temporal smoothness. Together, these losses optimize both intermediate and final video quality. In our experiments, we capture scenes using an event camera with motorized aperture. Turning the aperture on and off generates aperture modulation triggered events, providing data for evaluation. Here are our results on real captured datasets. The results show that our method reconstructs static backgrounds and dynamic content more clearly than prior approaches. Dense event information from aperture modulation significantly improves visual quality. Are our results on EVA datasets. Thanks for listening. You can visit our pages for more information.